Question 6, a ball is thrown vertically upwards from ground level with a speed of 20. Find the height to which it rises. Okay, 6A is 20 meters, that's the answer. And I want to talk about 6B. 6B. Find its speed when it is 2 meters above the ground level. So we take two snapshots. First is when I throw it, I'm giving it a velocity of 20. That's the initial. And the mass is not given, right? So I just write m here. Okay, when I throw it halfway to 2 meters above the ground, what is the speed here? What is the velocity here? Okay, first, is the mechanical energy conserved or not conserved? Mechanical energy is conserved when there is no external forces, right? So here, there is no external forces. There's no engine force. There's no pushing, no friction. So it is conserved. So I can write PE plus KE is equals to, this is before, and equals to PE plus KE after. Okay, so before PE is 0, KE half m and then 20 square equals to PE after it has gone 2 meters up. This is not the maximum height. The maximum height is way above 20 meters. This is just halfway. So we take the PE at this point would be m and then 9.81 mg h, so 2 plus, and then we have half m v squared. Okay, do some simplifications. We have 200 m. We leave the mass unknown, equals to 9.81 times 2. We have 19.62 m and plus half mv squared. Okay, now this one I bring it to the left. I get 180.38 equals to half mv. I forgot the m, mv squared. Cancel off the m, so you don't need to know the mass. Then you can find this one times 2. We get v squared equals to 360.76 and v square root. Then I get the answer, right? 18.99. You can just write 19.0 ms minus 1. Okay, so that's question 6b. Conservation of mechanical energy. Next one is question 7b. Okay, a marble is dropped from a height of 80 cm above the ground. Find its speed as it reaches the ground. Okay, when I drop it, initial u is 0, right? So find the speed when it just before it hits the ground, then you have to do the Suva equation. Okay, the v equals to u plus at, that one. Okay, we are not going to go through that one. You already know how to find it, so you should be able to get 4 meters per second when it is just before it hits the ground. Okay, now and then the question wants the ground that the marble falls on is muddy, and the marble sinks 2 centimeters into the mud. Okay, so when it hits the mud, here is the velocity is 4 meters per second, and it sinks 2 centimeters deep here, and finally it comes to rest. The question asks, given that the mass of the marble is 10 grams, and then find the average force exerted by the mud on the marble. Okay, exerted force, average force exerted, that is external force, right? When it hit, external force. Okay, we can use what we learned in the work energy principle. What does it say? When you have a force and a distance, work done, that is going to change the kinetic energy of the body here. Now, of course, you have to make sure that the system, there is a change in kinetic energy. There are some systems where kinetic energy will remain constant. So it's like when it's moving at constant velocity, then that is like no change in kinetic energy, then we cannot use this one, right? So in this example, potential energy, I'm not going to look at it because there's only change in the kinetic energy, right? When it sinks here. So W is the force exerted times the distance equals to the change in kinetic energy. I can just write half m, so 10 divided by 1000 v square, right? mv square. So this v is the change in the v, 4, and then comes to stop, 0. So up here, the kinetic energy up here is equals to 4 square, like this. Kinetic energy down here is 0. Okay, so I just take half mv square here. Okay, 10 divided by 1000 times 4 and then divided by 2. We get 0.08 force times. This is 0.02. And then we have force equals to 4 Newton. When the ball hit the mud, the 4 Newton force is exerted first by the ball on the mud. F ball on mud. Due to reaction, it exerts the same force on the body, on the ball. So F mud on the ball. These two are equal. Okay, so the force that you calculated, which one is this one over here? So if you use, like, for example, there are a few ways to calculate this. This is using formula. Not formula, using energy concept to find the force. You can use F equals to ma. Okay, you can use the Suvat, the V equals to U plus AT, you get the acceleration, then you get F equals to ma, you calculate the F, right? So in some cases, in that case, you will get like a negative F. You get a negative, like F equals to -4. Simply means that the force is acting upward, this force here. Okay. Okay, so that is for question 7b. Okay, let's go to the drawing board. Okay, so we'll start the lesson today. Today we'll talk about power and efficiency. Okay, power. Now, power, put it simply, it is the rate at which work is done. Now, before that, the previous lesson, okay, I forgot to post the recording of the previous lesson. Later, I will post it in a group. I already uploaded it. I post it, and then you can rewatch back. Especially Carlos, your new student here, you can watch back the previous lessons that we just entered energy. So last lesson, we talked about the work energy principle, right? If you have work done on a body, you have change in kinetic energy. This work done is, as long as there's a force, there's distance, then we count it as work done. We don't care about whether it is external or internal force, whether it is conservative or non-conservative force. And then another apart from this, we have another one is the external work done is going to increase the total mechanical energy of the system. Okay, so these two we discussed in detail in the last lessons, so you can rewatch back if you forgot. Now today we'll moving on to the power. Now power is the rate at which work is done. If a machine is doing work, we can calculate how much work is done by the machine in a given time period. You see, what is a powerful machine and what is a less powerful machine? What's the difference? The difference is here. I set a time limit. Let's say I have 5 machines. I give it a time limit of 10 seconds. Every machine only have 10 seconds to do the work for me. Whichever machine that does the most work in this time limit, then I would say that machine is the most powerful machine. Right? So you see, what is the common here? The common thing here is that all 5 machines, they have 10 seconds. So time is the common characteristics that we given here. Right? So same time, how much work done? That gives the power of the machine. So power is just energy. It's the same thing, just that we give it a restriction of time. Okay, it's the same thing as energy, just that we give a restriction, and that restriction is the 10 seconds is the time. Now, the machine that does the most work, it can be either produce the most force or it can produce the most displacement. Okay, because force displacement is work done. Now, take a machine. If the machine given t seconds, it can do this amount of work, W. So if I want to calculate how much work that the machine can do in 1 second, then I write 1 second, then I will use W divided by T, and here we get our power formula. So P equals to W over T. If T equals to 1 second, then you see power equals to W. So power is actually the same as work done, just that there is a restriction of time here. Okay, so P equals to W over T. Now, this is the general equation, and then also we have another equation for power. Okay, and here, this equation applies for if the work done or the distance is not given to you. For example, like a moving train. A moving train, the force is applied or produced by the engine of the train to propel it forward. Okay, how do you calculate the power generated by a moving train? Because you see, if you want to calculate power, you need work done, you need time period, right? So to get the work done, you need the distance traveled. How about if there's a train that moves at constant velocity and it keeps moving? It does not stop. If it does not stop, meaning that you cannot find the distance, right? Because you need time start and time end. You get a distance, then only you can calculate your work done, right? So in the case of a moving train, a moving car, anything constantly moving, how do we get the power? So in that case, that's why we have this formula. We do a little bit of adjustment. P equals to work done is force times into displacement, and then divide by T, and we separate this. Force equals to displacement. Oops, sorry. Force equals to displacement over T. So this is my velocity. So P equals to F times into velocity, displacement over time. Then we get our second formula here. P equals F times into V. This, we use it when an object is traveling at a certain speed and the work done or the distance is not given, just like the moving train. So Force is the engine force exerted by the train, and velocity is whatever the velocity that is moving at. So we don't have to know the work done. We don't have to know the distance. We don't have to know the time taken. We just have to know what is the force produced and what is the velocity that it is moving at. Okay, so two formulas, this one general and this one power. Okay, let's look at an example. Suppose that there is a car moving at velocity 30 meters per second, and there's a resistive force, drag of 1,500 Newton. This resistive force, the drag, depends on the speed of the car. It is not constant. It depends on how fast you're moving. If you move very fast, then the resistive force is very high. Okay, so this varies with speed. Now, say that it is 1,200 kg moving to the right, and there's a force produced by the engine of the car. If I want to calculate the force produced by the engine of the car, how do I calculate it? Let's say that this car is accelerating at 1.2 meter per second square. If it's accelerating at this much, then calculate the force produced by the engine. Okay, first we get the net force. Okay, net force. So we have here F equals to ma, Newton's second law. Net force, this one is equals to the resistive, or the engine. The engine should be larger, minus the resistive force, Fr, equals to ma. So 1200 into 1.2. Okay, so this one is 1500. So we can calculate the engine force, Fe equals to 1440 plus 1500 equals to 2940 Newton. Okay, so this force is the force produced by the engine to propel it forward. Now, let's say B, number 2. The question asks, okay, how do I find the power of the engine? Now we got the force from the engine. Simple formula, P equals to F times into V. So what is this force here? Is it the resistive force? No, not the resistor, not the resistive force, not the net force. It is the force from the engine. So equals to 2940 times into 30. Okay, so 2940 times into 30. We get 8820 watt. Okay, simply means, what does this mean? Meaning that every second it is doing a work of 8820 joule, okay, per second. 8820 per second. What is 1 joule, by the way? 1 joule, work done, right? You see, work done equals to force into displacement. 1 joule, you can think of 1 joule as, okay, there's a little bit lagging. Let me check again. Okay, should be okay now. Now, 1 joule, you can think of it like you take 1 kg object. No, you take like a 0.1 kg. This is 0.1 kg is 1 Newton, right? So you take 0.1 kg object, you move 1 meter up. That is 1 joule, just to give you a perspective. Okay, how much is 1 joule? So you take 0.1 kg object, you move it up 1 meter. Okay, so that is 1 Newton times 1. So you get 1 joule. How about 1 watt? 1 watt. 1 joule is like you move 0.1 kg up 1 meter. 1 watt would be you do this in 1 second. Okay, so power is a energy with time, right? So you do this in 1 second, that is equivalent to 1 watt of power. So this engine is doing 88,200 joule per second, 88,200 watt. Yeah. Now you see, when the car has an acceleration, right? 1.2. So if the car continue to accelerate, what happened to the resistive force? The resistive force will increase because there is acceleration and velocity will increase. As velocity increase, this will also increase. How about the force from the engine of the car? This force increase, right? How about the force from the engine of the car? I can write the equation net force is equals to the engine minus the resistive force, right? This engine force is a constant force, correct? It does not change. We assume that it is producing constant force, but this one is a variable force. And it depends on the speed. If the speed high, then Fr will also be high. So when the car is accelerating, then this Fr will gradually increases. And what happened to the net force as this Fr increases? This Fr increases, and this Fe minus Fr becomes smaller and smaller and smaller and smaller, meaning that the net force becomes smaller. As the net force becomes smaller, what happened to the acceleration? The acceleration drops, right? So this will become smaller, and as F net becomes smaller, acceleration will also drop. And at one point, the car will have 0 acceleration. That is when the Fe minus Fr become 0, right? Becomes 0, meaning that the resistive force is the same magnitude as the engine force. That is when acceleration equals to 0. Okay, at this instance, what happened to the car? We said that the car has reached its maximum velocity. Okay, based on the setting, based on the engine force, assuming that we don't change it, if that is the maximum power that it can give, then this becomes the maximum velocity that it can achieve. Okay, so the maximum velocity of the car or of any vehicle can be achieved when there is 0 acceleration. Okay, is that velocity 30 meters per second? No, 30 meters per second is when there's still acceleration. That is the initial. We are talking about now the velocity has increased to a new value here. Okay, so that is how the resistive force affects the maximum velocity of the vehicle. Okay, now at this stage, the forces are balanced, right? So work is balanced. Remember, when the car reaches maximum velocity, let's say V, whatever the velocity is, maximum, V max, it is constantly moving at this velocity. And since it is moving at constant velocity, that means that there is no change in kinetic energy. So the work done on the car by the engine is the same as the work done on the car by the resistive force. This is doing positive work. This is doing negative work because the car is having a displacement to the right. So this is same direction, positive work. This is negative work. Okay, so this give this amount. Doing positive work, I give it a certain amount of kinetic energy, but the air resistance is doing negative work. It takes the same amount away. That's why it is moving at constant velocity. So this one, we can also say that the power generated, because power is just work done, right? Power is just work done in 1 second. So if you think about this scenario in 1 second, then you get power. It's the same thing. So we can also say that power generated by the engine here is used to overcome the resistive force. Okay, power generated by engine is used to overcome resistive force of the air around it. So there is no increase in kinetic energy. Okay, per second, maybe I can say per second. Now, continue. Until here, let's say the car reaches maximum. So it reaches moving at constant velocity, and you can calculate the power, okay, the power. Now, let's say the car move up a slope. Okay, I don't have enough space. You can take down this and I go to the next slide. I want to erase this. Okay, let's say we have the same car. Now the car moves up a slope here. And let's take it as, okay, 10 degree. 1,200 mass is the same. And it is moving, say that it is now moving at a velocity of 10 meters per second. Up, constant, okay? Constant velocity. So it's still experiencing a drag, but the drag is not as much because it's now moving relatively slower. So this drag, let's say, is 500 Newton. Calculate the power generated by the car right now. Okay, we calculated power just now. That is when it's moving at horizontal row. So if it climbs up, then it is exerting a different amount of powers, and we want to calculate that one. Okay, to calculate the power, again, we have the formula P equals to F times V. What force is this? This is the engine, right? Velocity has already got. So all you need to find is just the engine. How do I find the engine force here? Okay, forces are vector. You have to label all direction first. Engine force is parallel to the sloping ground. This is Fe. Okay, and then we have drag 500 pointing at this direction. So if I move the place, just change the force here. And let me erase this. Okay, and then we have what else? We have mg, right? Mg here, and also we have reaction R. Considering all forces, and you have to resolve here. You have to resolve because the total forces that is dragging the car is not only from the resistive. If you see the car is moving slope upward, right? It's very easy to think, oh, all the forces dragging it is just the resistance. No, because it's sloping, right? So there's another force component that is dragging it down. It is the mass of the car because of this position. So the mass of the car try to drag itself. Okay, its own weight tries to drag itself. So meaning that you have to resolve this mg. Okay, so resolving the mg, we have here Fe equals to 500 plus the mg sine 10 degree. Okay, so equals to 500 plus 1200 9.81 sine 10. Okay. 200 times 9.81 sine 10 plus 500. Okay, answer is 2544.19 Newton. This is the force exerted by the engine when it is moving up the ramp. So power equals to 2544 times 10 meter per second. Equals to 2544 2 watt. Here. This is my power generated by the engine. Okay, then question asked again. Calculate the power. Calculate the power used to overcome the resistive force. What's the resistive force here? Here we will not consider the mg. The resistive force, it is referring to the 500 Newton. Okay, so we calculate the work. This 500 Newton is doing negative work, right? Because the car is moving up, the force is opposite direction. So we can calculate the negative work of this, or we can also calculate the negative power. Okay, because work is just power, so I can just call it, I can calculate the same way. Power equals to force into velocity, that is 500 into 10 equals to 5,000 watt. This power is from the air resistance, the drag. Okay, you can also say that it is taking this much power away from the car. So meaning that this car has this much power is doing against, how much power is doing against the resistive force? 5,000 watt. Yeah. Now, then what is the rate of change of PE then? What is the rate of change of potential energy? In this example, what happened to the kinetic energy? The kinetic energy does not change. Same constant velocity. The moment it rises, the moment it moves up the slope, it maintains constant. So KE would be 0. There is only a potential energy change. Okay, so but we want to calculate the rate of change. What is that? Rate of change is another word to refer to the power, right? Rate of change of energy. Power is just rate of change of energy. So we want to calculate the rate of change of potential energy. Then we calculate potential energy gain per second. That is energy per second, right? Energy per second is equal to useful power. You see, this is the power generated by the engine, right? And this is the power used by the engine to overcome the force. So what is the useful power here? You take this minus this, that is the useful power. And that useful power is being converted to the change in the PE, right? Change in the PE. So we calculate P useful equals to 25,442 minus 5,000. We get 20442 watt. This is useful power, meaning that the car engine is doing 20442 joule of work per second. Or I can also say that it is converting 20442 joule per second into potential energy. Right? So the rate of change of potential energy is 20442. This is your answer. It's the same as the power. Okay, now here we want to calculate again what is the height reached after 6 seconds. What is the vertical height reached by the car after 6 seconds if we can maintain this useful power over time? Every second it is converting this much of energy from chemical in the engine into potential energy. How about the kinetic? The kinetic does not change, right? Maintain. So the conversion only happens between the chemical and the potential. And here we use this power to calculate what is the height reached after 6 seconds. So you just find after 6 seconds how much energy it has converted into PE, right? So 6 seconds times into the power 20442. So in 6 seconds, 20442, a total of 122652 joule of energy is converted into potential. So from the PE, mgh 122652 equals to 1200 9.81 and times into the vertical height. And then we just solve the equation. Okay, 122 10.42 meter. Okay, so after 6 seconds, it would have risen 10.42 meter from the ground. All right. Okay. And I just show you one example here, and I have a few more. You can take this down, and I go to the next one, and you try it. The next one. Okay. Okay, guys. Example 6. I'll give you a few minutes, and then we look at the question, the answers. If you have answers, you can let me know in the chat. Five one eight zero, 51480. Okay. There is a change in mechanical energy, right? You can use that to calculate. Power equals to work divided by time. Okay, what is the work done here? First, we are going to make an assumption. Assuming that the pump works at steady rate, meaning that every second it is converting the same amount of energy. Okay, we don't want it to, this second it's converting this much and the next second is another different amount of energy. So we assume that it works at steady rate. So the pump is doing the work on the water, right? So work external, the external force, okay, by the pump is equals to the change in mechanical energy. So the water is going to gain mechanical energy. First, we calculate what is the change in kinetic. Half mv square. The change in kinetic is, first, it is at rest, and then it raises up with a speed of 6 meters per second. So half times 600. Now be careful, this 600 is every minute, right? The pump moves 600 kg of water every minute. So we are calculating minute here. Okay, minute. Now here, half times 600 times 6 meters per second, okay, square, equals to, this one we get 10800. This is the amount of kinetic energy it gains from the pump. The pump is doing work on the water. Okay, how about the potential energy? Right, change in potential energy equals mgh. Again, 600 times 9.81, and then we times by 4 meters equals 23544 joule. Increase in Ke and increase in Pe. Total increase, the change in mechanical would be 10800 plus 23544. 34344 joule. This is per minute, right? Per minute. All this, they are per minute. So we are calculating work done or the energy gain, the total mechanical energy gain, but per minute. Okay, so who is doing the work? The work is done by the external force from the pump. Now, to calculate power, then we just put in the equations here. P equals to W over T equals to work total. This is the total energy. So 34344 divided by, this is per minute, right? We want per second, so divide by 60 equals to 572.4 watt. This is my answer. Maybe I can approach it to 572 Newton. Three significant figures. Yes. Oh, sorry, my mistake here. This is watt. Why? Okay, next one. Example 7. Again, 5 minutes. We try it first. For the second part, I add 1 here. We take the assumption of assuming the same resistive force is acting on the car. When it travels up the incline, assuming that the same resistive resistive is acting. Okay, if you have answers, let me know. For A, you have to get the force of the engine first. It says maximum speed. That means constant. Okay, let's look at the solution. Yeah, I see some correct answers. 9,000 watt, 14.4. Yes, that's correct. Okay, for 7A, find the power of the car's engine. It says that maximum speed, right? So force must be balanced. Resistive force is 450. Engine force balance. So it's also 450. It is at max or constant speed. So P equals to F times V, 450 into 20. 9,000 watt. Second part, the car is traveling up a road incline at sine -1, 0.02. So here, sine -1, 0.02 to the horizontal. Okay, with its engine working at the same rate. So the power is the same. P equals to 9,000 watt. Find its maximum speed. Take G equals to 9.8. Okay, again, maximum speed, force balance. Right, so this is the draw the force. This is very similar to the questions that we discussed earlier. We have mg, we have the drag, and the Fe, engine, and the reaction. Balance force Fe is equals to d plus mg sine -1, 0.02. This one you can just cancel the sine and the sine. Sine -1, you just can cancel it, you get 0.02. So Fe equals to d plus 0.02 mg. Okay, put in the values. So same, we assume same resistive, 450 plus 0.02. And then we have the mass of the car, 900 into 9.81 equals to 626.58 Newton. Okay, so P equals to F V 9,000 divided by 626.58 is your maximum velocity. So 14.3636, you can approach it as 14.4 m/s. Okay, so as usual, you get your 3-minute rest and we will continue in 3 minutes. 8:07. Okay, guys, we're back and let's continue. Okay, just a short one. This one, efficiency of a machine. After we finish this, I have exercise for you, and for the coming lessons, we'll keep doing the past years. Right. So efficiency of a machine. What does a machine do? A machine convert one form of energy to another form of energy. So that is, it is doing the work. In that work, one form of energy is being transformed into another form. Now, we design machine to do the work we need. We design machine to do work for us. Example, what do we need? For example, if I want the work to be done in which the water is raised up to the top of the roof, then we design a motor, a pump. If I want work to be done where the heat in the room is being taken outside, is being removed outside, we design another machine to do the work for us, and that is the air conditioning. Right? If we want to create mechanical motion, we want movement, then we design engine. That is also a machine. We design engine that converts chemical into movement. So everything around us, the machine help us to do work, and it do work for us. Every time it does work, energy is being converted. In the process, energy is always available around us. We are just utilizing the energy around us that we have, and we create this machine, this device, to help us convert one form to another form, meaning that energy is never created. A machine cannot create energy by itself. It takes available energy in the surrounding and converts to another form, and then in the meantime, there is work done. Okay, now, what is mean by efficiency of a machine? Energy is always converted. We understand that already. And here I have a machine. First, I have to give work to the machine. I have to give energy to the machine, because by itself, it cannot have energy. It is just a device that converts. So I have to give it a energy, and we call that energy input, right? So energy input, we give it electrical energy. Okay, we give electrical energy to the pump, and then the pump takes the energy to convert it into potential energy, and then the water is raised. Now, this work is done two processes. First, I do the work on the machine, and then the second process is the machine do the work on the water. Now, whenever work is done, energy is being converted. So chemical, whatever energy that I'm giving it, okay, it could be electrical energy, and then that electrical energy eventually goes to potential energy. Now, whenever the machine raises the water, we calculate what? We calculate the MGH. We calculate the height, we calculate the mass, how much it raises. This calculation is the work done by the machine. So one is work done on the machine, that is the energy input. And when the machine is doing the work, it raises the water, then the one that we calculated is the energy output. It is the work done by the pump. So two energies here. First is energy input, and then we have energy output. Okay, now they found that these two are not equal. Why is it not equal? Because based on the conservation of energy, energy should be equal, right? But why is it not equal? The answer is this: whatever is the input, it is not necessary that all will transform into what we want. What do we want? I give it 100 joule of electrical energy, and I want the pump to convert the 100 joule into potential energy and raise the water to the maximum height. That is what I want. I want all 100 joule to be converted to 100 joule. But there is a friction in the motor, in the working of the motor. And since there's friction, the motor gets heated up. Okay, it gets heated up, and then there's a heat radiated out from the coil of the motor. This one will be discussed more in detail in the thermodynamics. There's always radiation of heat. Okay, there's always friction, there's always radiation of heat. You cannot escape from this too. So this energy required for the frictions and the heat radiation, we call it the energy loss. It is the energy required for the pump to operate itself. Okay. Now, the loss of energy, why do we call it loss? Is it really means that it is lost, like gone already? No. Loss does not mean it is destroyed. Okay. Loss just means that it has converted to something I do not want. What do I want? I want 100 joule of electrical go to 100 joule of potential energy. But it converts 20 from the 100 goes to heat energy. That is not what I want. We don't want heat. I want 100 to go to potential energy, right? So because I'm not getting what I want, so for me, I would call it a loss. Okay, so that's why I call it lost energy. There is a lost energy as heat. So based on this, that is why energy output is always lower than energy input. Energy output is always smaller than energy input. So this always less than the denominator. Suppose that I give 100 energy to the pump, and it only does 60 joule by raising the water. It does 60 joule. Then efficiency becomes 60%, or you can write it as 0.6 like this. We give this efficiency a symbol of eta. Okay, eta. Now, energy is the same as power. If I take this divided by time, this divided by time is the same thing. I can cancel off, I get back the same fraction. If I divide it by time, then I get power output, and divided by power input. Okay, efficiency equals to power output divided by power input. Or you can use energy output divided by energy input. Okay, so understand that power and energy, they are just the same, just energy per second. So no machine in the universe is having 100% efficiency. Okay, because there is always radiation of heat going on. All objects, they have the tendency to radiate heat as long as they have temperature. If an object has no temperature, then only it will not radiate heat. What is temperature? Temperature is just the vibration of molecules. Okay, so as long as molecules keep vibrating, then there is radiation being emitted out, and there's energy loss to the surrounding. Okay, unless you cool it down to like absolute zeros. Okay, lowest temperature, then there's no radiation. So since temperature is always there, radiation is always there, then there's always heat loss. Okay, because all the molecules, they never stop vibrating. Every object, they have certain temperature, they have certain radiation. That is why we don't have 100% efficient machine. Okay, so that is for a short lesson on efficiency. This is actually nothing new. We learned before, right? All this. All right, guys, I'm going to give you some practice, power and also efficiencies work done. I want you to do it in the class and also submit to me after you finished. Okay, I want to mark it and give it back to you. Okay, give me